Welcome to the fifth and final part of Unit 6. In this part, we are just going to be working two examples of Newton's second law. To begin with, I wanted to give you a methodology for solving these problems. First things first, draw a picture. Second thing is determine what the problem is asking for, because depending on what the problem is asking for is going to influence potentially how you draw your free body diagram. Okay, on your free body diagram, make sure you include a coordinate system. Define your positive directions. Label all your forces. Now, I outlined how I use a set of subscripts. To me, it doesn't matter how you call your forces as long as it's clear to you. I will expect you to be able to identify those subscripts, what's causing this force versus what's experiencing it. Next to your free body diagram, include the expected direction of the acceleration so that you can expect, hey, am I going to get a positive number out? Am I going to get a negative number out? It just helps you organize what you're doing and what you're thinking about. Resolve any forces into components based upon your coordinate system. That will come into play in future examples, will not come into play for this unit. Once you've done that, apply Newton's second law in both directions, both the horizontal, typically the x direction, and the vertical, typically the y. In this unit, while we may have forces going in both directions, we will only need to use Newton's second law in one of them. And because of that, there's not going to be any simultaneous equations you need to solve this unit. However, it is perfectly reasonable to expect them in the future. So the first example we are getting to is the rocket sled. This is an example directly out of your book, which is why it references a figure, because I just typed it verbatim. So in the figure that you can't see, you have a rocket sled. Okay, well, my rocket sled is actually going to be on wheels, and it has 4 rockets. 1, 2, 3. Oh, goodness, the last one looks like it's going in the ground, but that's okay. It starts with only 1 rocket burning. So the top rocket is burning there. And it wants to know what is the acceleration. And it gives you some numbers. Assume that the mass is 2,100 kilograms. The thrust is 2.4 times 10 to the 4th newtons. And the force of friction opposing the motion is 650 newtons. So that's question, or part A, question 1. Why is the acceleration when 1 rocket is burning not 1/4 of what the acceleration would be with all 4 rockets burning? Okay, so following our steps for solving these problems, I've started my picture here. I'm going to toss on a coordinate system. Makes sense to let the direction of the acceleration be to the right, and therefore the positive x direction be to the right. We know we have friction, which will oppose the motion of the sled, so friction's going to go backwards. Okay. Next thing on the list of things to do is identify what you want to know. Well, we want to know the acceleration. So a free body diagram of the sled is what I need. So let's draw that free body diagram. So I have a normal force from the ground on the sled. I have the sled's weight pulling down, but there's no acceleration in the vertical direction. So I can just automatically say these two are equal to each other because it is not accelerating. Okay. I also have the force from the rocket on the sled, if you will, and that is propelling the rocket sled forward, so I put it that direction. And then I have the friction between the ground and the sled opposing the motion. Things that I know. I know that this one is 2.4 times 10 to the 4th newtons because there's only 1 rocket firing. And I know that this one is 650 newtons because I have friction at a known value there. So taking all of this information, I can now find the acceleration for the sled when one rocket is burning. To do that, I'm going to use F net equals ma, and this is only in the x direction, so if you want to put an x here to indicate it, you can. I'm going to rewrite that in terms of the forces on the sled. So remember that the force from the rocket on the sled was in the direction of the motion, in my positive direction, so therefore I put it down and then subtracted off the force in the other direction, which is friction. That has to equal ma. And now I can plug in numbers. 2.4 times 10 to the 4th newtons minus 650 newtons is 2,100 kilograms times the acceleration. Or in other words, 2,100 kilograms multiplied by the acceleration has to equal 2.335 times 10 to the 4th newtons. So the acceleration is that number, 2.335 times 10 to the 4th newtons divided by 2,100 kilograms, and I get an acceleration of 11.12 meters per second squared. I'm going to label this an A with a little subscript of a 1 to remind myself that this is the acceleration with just one rocket or whatever burning. The next part of the question asks, well, compare this acceleration to the acceleration you get with all 4 thrusters burning, and why isn't it what you might expect it to be? So let's go to the next part and redo the math for the 4 thrusters. So now instead of having one force, I have 4 times the force of the rocket on the sled minus the friction between the ground and the sled has to equal ma. Well, that works out mathematically to be very similar to what I had in the previous slide. So 4 times 2.4 times 10 to the 4th newtons minus 650 newtons equals 2,100 kilograms times the acceleration. And if I take and multiply this out and subtract the 650 and divide by 2,100, very similar to what I got in the last slide, I get the acceleration in this case is 45.40 meters per second squared. And I'm going to subscript this with a little 4 because it's for what happens when I have all 4 thrusters burning. What the second part of the question was really wanting was me to take A4 and divide by A1. So that's 45.40 meters per second squared divided by 11.12 meters per second squared. And if I do that math, 45.4 divided by 11.12, I get just over a factor of 4 different, 4.08. Well, why isn't it exactly 4? I mean, I multiplied the thrust by 4, so, okay. Why isn't it exactly 4? And it all comes down to the friction. So why not exactly 4? And that's because the friction, FGS, is constant. It was 650 newtons when one rocket was burning, and it was 650 newtons when 4 rockets were burning. And therefore, that affected the acceleration. Okay, on the second example, This is from the great sport of curling. Okay. For those of you who haven't observed curling, it is an Olympic sport, and you have a sheet of ice. You have players on each team, and what they do is they take a large stone, actually looks like a big, very nicely polished stone. It's got a little handle on the top. And there's one player that sets the stone going down the sheet, and there are other players that come in and sweep the ice and affect the motion of the stone as it goes down the sheet. And the idea is that there is a set of rings at the far end, and you want to get as many stones as possible, as close to the center as possible, compared to your opponent's team. And you can, hit their stones and knock them out of the way and do all sorts of fun stuff. We're going to ignore 90% of that for this example. Okay, what we're going to do is we are going to assume that the stone is going down the curling sheet a distance of 40 meters, which is a reasonable distance for a curling sheet. It takes 8 seconds to do that motion. We're going to assume a constant acceleration, so the sweeping and any of that is happening, we're going to ignore essentially and simplify the situation. And the question is, what is the force of friction between the ice and the stone in this case? Okay, so we've got a picture. It makes sense again to let acceleration be in the direction of the motion. So I'm going to, not acceleration. Let's try this again. To let the positive direction be the direction of the velocity, but that means our acceleration is going to be in the opposite direction, so our acceleration will be negative in this case. That'll work. We can make that happen. Okay? If we draw the stone's free body diagram, we have the normal from the sheet of ice on the stone. Now, SS is a little confusing for our subscript, so instead of using sheet, I'm going to use ice and stone. We have gravity pulling downward, but again, it's not accelerating in this direction. This stone isn't going to magically fly off a sheet of ice. It's going to stay right where it is vertically. So these two are equal because it's not accelerating. Horizontally, we've got one force, and that's the force of friction between the ice and the stone. Remember, all this analysis is taking place after the person has set the stone into motion. So there's no force pushing it any longer. It's just going. Okay. What we know is we know F net equals MA. And I can rewrite my net force in terms of, and remember up here, we defined this direction as positive. So I'm going to subtract off my force of friction because it's not in my positive direction, and set that equal to MA, which means the force of friction will have a magnitude given by negative MA. Okay, that's all fine and crude. I know the M, it's 18 kilograms. What I don't know is the acceleration. But look at the information I'm given. I'm given a distance. I'm given a time. If this weren't a question about force, you could find that acceleration. If I gave you the question with everything, but just change the last sentence, assuming a constant acceleration, what is that acceleration? You could do it. And how would you do it? Well, you would do it with kinematics. Right? So now let's go back and think about this as a constant acceleration problem. So what we have is we have the pitch. We have our stone with its little handle at the top. It starts moving with an initial velocity. I'm going to define this direction as positive to go along with that velocity, which is consistent with what I did in the previous slide with the forces. It's going to be slowing, so the acceleration will point the other direction. I can let this position be 0. And where it stops down here be the 40 meter mark. And I know if this is t equals 0, this is t equals 8 seconds, given all of this information. I'm going to define my coordinate system with positive x going to the right, positive y going up. Not that we have any motion in the vertical direction, but consistency and things like that. Now I can define my grocery list. Okay, so t equals 8 seconds. The acceleration is what I want to know. My initial velocity, I don't know. I do know that it comes to a rest, so that's 0 meters per second for the final velocity. My initial position I set to 0. My final position I set to 40. Okay, I want to know acceleration. If I go back and think about the constant acceleration equations, all of them involve the acceleration, and all of them involve the initial velocity. So before I can find the acceleration, the first thing I need to do is try to get the initial velocity. Well, I'm not actually going to be able to get it. What I'm going to be able to do is get an expression for the initial velocity in terms of the acceleration. So I'm going to use the v equals v naught plus at equation. So 0 meters per second equals v naught plus the acceleration times 8 seconds. Or in other words, v naught is going to be negative a times 8 seconds. Okay, I know it doesn't look like it helps, but it actually does. And now I can pull out the x equals x naught equation. I have x equals to 40 meters, x naught equal to 0 meters, plus my v naught from above, which was negative a times 8 seconds. All of that multiplied by t, so it's multiplied by another 8 seconds, plus 1/2 times a times 8 seconds squared. Okay, so 40 meters equals negative a times 8 seconds times 8 seconds. So that's negative a times 8 seconds squared plus 1/2 a times 8 seconds squared. Or in other words, it is negative 1/2 a times 8 seconds squared. Negative 1 plus 1/2 is negative 1/2. That all equals 40 meters. Which means that a equals 2 times 40 meters divided by 8 seconds squared. There's a negative sign out front, don't want to drop that. And if I put that all into there, I get an acceleration of negative 1.25 meters per second squared. It is negative. I expected it to be negative because that's how I set up my coordinate system. Now that I have the acceleration, I can bring that back to this slide, and I get the force of friction is, I don't want to put an m there. I want the 18 kilograms. 18 kilograms times negative 1.25 meters per second squared. And if I take 18 times 1.25, I get 22.5 newtons. Okay. So the magnitude of the force of friction is 22.5 newtons. Now you may be wondering, you may be looking at this and going, but the force of friction is not in the positive direction, it's in the negative direction. Yes, I agree completely. But we've already put that negative sign in. That negative sign is right here. When we subtracted that force of friction, we were saying, hey, this is the negative times the magnitude. And when we calculated the magnitude and got ourselves out a positive number. This concludes this part. It also concludes this unit. In the next unit, we are going to be expanding on our study of forces by bringing in Newton's third law, which allows objects to interact with each other.